Here is a nice word problem that we can solve. We're told about an alcohol being treated with HBr yields a mixture of 1 bromopent-2-ene and 3 bromopent-2-ene. So let's look at setting up this problem. Alcohol, HBr, we've got 1 bromopent-2-ene, so there's the 1 bromo. The alkene is on the second carbon and the third one, and then we have another possibility, this isomer. And if you remember from the alcohol, or actually the alkyl halide chapter, substituting an alcohol with a Br just involves protonating with HBr potentially, and putting a Br on in place of the alcohol. And so we're also going to produce water as a byproduct here. I'm not sure that's important to solving this reaction, or this NMR spectrum, but it is still good to have a complete formula. Balanced equation, I should say. So another thing we can do is to figure out that the formula of the alcohol is C5H with a single O. And because we don't expect the HBr to affect the number of alkenes, maybe the location of alkenes if we do some resonance. That's always a possibility when we have strong acid. We're protonating OH, making water, losing water, creating a cation. So there's the possibility that the alkene has moved, and we can see that from here. So let us look at the formula. C5, definitely 1, 2, 3, 4, 5. The number of hydrogens should be 3, 4, 5, 6, 7, 8, 9, plus 10, the hydrogen on the oxygen. So I'm betting this is a H10. And then, of course, we have an oxygen. That gives us this formula, C5H10O. It does match the HDI that we'd expect. So let's proceed on the assumption that we have C5H10O. We can look at the carbon NMR spectrum, and we see a number of peaks. First, I want to point out that this peak here at about 77 ppm is CdCl3. So let's make a note of that. That is chloroform that has had a hydrogen replaced with a deuterium. That's typically a very common NMR solvent, which we replace the hydrogen with a deuterium so it doesn't show up in the proton NMR spectrum. Of course, we didn't replace the carbon with a non-C13 containing carbon, so this does show up here. It actually is a 1-to-1-to-1 triplet, and that is because the carbon couples with the deuterium in a different manner than what we're used to with normal 1H type spectra. Also, this signal at 0 is TMS. So let's make a note of that. Sometimes when you're presented with a spectrum, the instructor will cover up this signal at 77 ppm so that you're not distracted by the CdCl3 signal. Other times they'll just expect you to recognize that it's a 1-to-1-to-1 triplet. It's not part of the sample, it's the solvent. So don't be distracted by those. That leaves these 5 large peaks, which confirms that I have at least 5 carbons in my alcohol formula. And probably I have some alkene type carbons and maybe a CO carbon right here. That makes sense. I expect to have an alkene in my formula or my structure. I expect to have a CO bond, and then I expect to have a couple of carbons that are not attached directly to COs. Okay, let's look at the proton spectrum, and I count, again, this signal is TMS, so there's a signal here, 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 here. So I have 5 signals. I'm told that the signal at 1.3 is a doublet. I've got sort of a mess here at 2.2. I've got what looks like a pentet at 3.7, and then I've got some messes at 5 and 6. Those are probably the alkenes. Let's go ahead and label these A, B, C, D, E. And then also let us define the integration. So remember that I have 10 hydrogens to integrate with. Probably the difference between, or the height here, corresponds to 1 hydrogen. And that is sort of similar to what we get here. And that's definitely what we got here. So I'm going to go ahead and label this 1H, this with 1H. If I look at this difference, compare it to this difference, and compare it here, this is probably 3 times and another 3 times. And again, these integrations aren't going to be exact, but they're going to be close enough that we can get whole number integers in order to add up to 10. And that leaves me with 2 hydrogens right here. Right, I have 1, 2, plus 6 is 8. I need 10. So I likely have 2 hydrogens right there. So let's do some deciphering then. The signal at E is most definitely a methyl group that is adjacent to 1 hydrogen, because it's a doublet. Okay, so that's the signal at E. I'm going to leave the signal at D for a while because you'll agree this signal here looks kind of messy, and that tells me it might actually be 2 different hydrogens that just coincidentally have very similar chemical shifts. So I'm going to leave it alone for a bit. I'm going to focus on this signal at C. What we can conclude from C is that it is 1 hydrogen, and it's next to, this signal looks like 5 peaks. However, generally on a 5 pentet, the last peak is much shorter than it appears to be right here. So I'm thinking this is actually a septet, 7 peaks, with a little tiny peak that we really can't see. It's so small that it doesn't really appear here. So I think there might be 6 neighbors in this case. There might be 6. I'm going to draw my CH here with 4, and we'll say that maybe there's some more. Maybe there's some more. So let's put an X group here. May have 6 neighbors. And again, that conclusion is not one that I expect you to be able to make after studying NMR for a week. That is a conclusion that you would draw after a large amount of experience solving these NMR problems. All right, so the last couple are A and B, and those are in the alkene region, 5 to 6 or 5 to 7. And this peak here at A looks like it could be 4 1-to-1 to 1-to-1 signals. And that's very indicative of a doublet of doublets, which is very commonly found on an alkene signal. So let's look at A. I think that A is probably, or A and B I should say, are these 3 hydrogens shown on this vinyl group. That would be the end of a chain. And so let's see, I've counted for A, B, C, and E. I have to account for D. And what do I have missing here? What do I have missing? I've accounted for carbon, 2 carbons, 3, 4 carbons. I'm missing 1 carbon. I've accounted for 3 H's, 4 H's, 5, 6, 7 H's. So I need 3 H's. So let's just make a note of that here. I can do that up here. So I have a C, 3 H's, and I believe an O. I have not accounted for the O yet either. So most likely all of those atoms here are producing the signal at 2.3. And we do have 3 hydrogens here. That makes sense. So if we're going to apportion these out, we know that we have an alcohol, right? So let's look at D. Let's propose that D is the OH and a CH2. Okay, so I knew that because I have to have an OH because I know that I have an alcohol here. And I have 1 carbon left and 3 hydrogens, and I need to make a 3 hydrogen signal. So this could potentially be an OH peak and a CH2 group. And so let's see if I have enough information now to put everything together, because I have some connectivity. Let's see. I'm going to draw everything now in just single pieces. I'm not going to draw any other bits. So that's E. C is a CH that has 3 attachment points, and then A and B are the vinyl group that has the 1 attachment point. So sometimes it's easy to just put everything together once we have these pieces. So we have 1, 2, 3, 4, 5 carbons. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and we have our O. So we have all the different pieces. It matched the formula that we expect to find. Now it's just a matter of combining these so that I can get the appropriate signals and everything else. So the one thing I want to do is I can attach immediately the methyl at E to the methylene or methine at C, because I know that the methyl at E is only attached to one carbon. So let me go ahead and attach that. And I have 2 more attachment points for this CH group. And I've gotten rid of the methyl, I've gotten rid of the CH group. And now I have a CH2, an OH, and the vinyl. And those are, yes, so another thing that we can look at is that the OH can only attach in one spot, and the vinyl can only attach in one spot. And so I think you'll agree with me that the OH is not attached to this vinyl group, because that would be a complete molecule. So I need to attach the OH somewhere so that it can, and I need to attach the CH2 as well. So I think the CH2 is probably here, and then the vinyl group. And that leaves the OH right here. And I could have attached the OH to the CH group, but remember my thought that it might have 6 neighbors, and we see now that it does have 6 neighbors. So I think this is a pretty likely possibility. Also, if I were to do this idea, I don't have 5 carbons in a chain, right? I have a branch point here, and this product has 5 carbons in a chain, and so does this product. So that gives me a hint that I probably don't have this branched chain. And I'm going to erase that so I can get some more room here. But hopefully that is another argument that will help you understand that this is probably the product that I have here. So then I'm going to redraw what I just did, but I'm going to use a stick drawing. So that's what I just erased. And I think you'll agree that if I mix this with acid, I will protonate and lose water to create this cation. And if I do a hydride shift, I can create a much more stable cation that is resonance stabilized. So I think this is definitely the structure that we solved using the proton and the carbon NMR here.